Okay. So, we start with a very simple situation. Alright. So, we start with a very simple molecule. What will we start with? H2 is boring. So, what I will do is I will start with a 3 atom molecule BeH2. What is the geometry of BeH2? Why? No, don't say that. We are actually going to not use hybridization in our discussion. Please understand something. The shape of a molecule is not because of its hybridization. Hybridization is a way in which we try to rationalize the step, the shape. The shape is because of VSEPR, valence shell electron pair repulsion. And did I say this in the course last semester also or not? So, what I am telling you is, next time you go to a birthday party of someone who cares to deck up the place with balloons, do this. Have you seen those balloons in a birthday party? Usually 4 of them are tied together, right? What is the shape? Have you noticed? Always. Provided the balloons are all of the same shape. Now, what I encourage you to do is that, under the pretext of celebrating the birthday, take off one of those tetrahedrons. Okay? Get a toothpick, which is also available in the party, right? Burst one of the balloons. In front of your eyes, that non-planar tetrahedron will become a planar trigonal shape. There is no sp mixing in the balloons, right? It's a steric effect. VSEPR is a steric effect. Just burst it, it will become trigonal in front of your eyes. Burst one more, it will become linear in front of your eyes. Hybridization is not the cause, that is what I am trying to say. Understand? Very often we think it is not. Hybridization is an explanation, is a way of explanation. That is not the cause. If hybridization at all takes place, it takes place to give you the right geometry. But the right geometry comes from that repulsion. Lone pair repulsion is more, and that lone pair repulsion is also not electrostatic repulsion. It is steric repulsion. Lone pair is bigger because it is not bound on one side. So, it is kind of spread over a bigger place. Okay, that is why lone pair repulsion is most, followed by lone pair bond pair, followed by bond pair. Okay, it is a steric effect, and this balloon experiment is the best way of seeing it. I think I talked about this in this course also. So, now you have burst 2 balloons, it has become linear. Now, what you do is you grab another tetrahedron and try to tie together the tetrahedron and this linear balloon. You will see that the balloons will shift and they will form an octahedron in front of your eyes. I have done it in many places, just that I tried to demonstrate it with some kids who are too young, and they completely hate me for bursting so many balloons near their ears. No, but I kind of got carried away and ended up bursting 25-30. So, you combine the tetrahedron with the linear combination of the balloons, it becomes an octahedron in front of your eyes. Now burst one, it will become TBP. Burst any, doesn't matter whether you burst one that was from the original tetrahedron or one that you have joined, it will become TBP. So, next time get invited to a kid's birthday party, carry a toothpick and do this experiment, it is fun. In any case, people will think that you are just celebrating. So, what we do here today is that we do not even talk about hybridization until and unless we need it. Okay. Rather, we use this concept of symmetry adapted linear combination. And we start with a simple system and slowly we go to a little more complicated system. So, BeH2 is a linear molecule not because of hybridization, but because it is an AB2 kind of system. There is no electron pair on Be. It is a pure AB2 kind of system, that is why it is linear. Okay, fine. So, what we do is we try to see which orbitals can participate in the molecular orbital formation and go ahead from there. So, you could take two approaches. First is you could use hybridization and generate what is called the localized molecular orbitals, but in any case I do not want to do that. So, we will focus on the delocalized molecular orbital all the way. Because that is the strength of MOT, isn't it? It allows you to handle more than 2 center 2 electron bonds. So, we better use the strength to the maximum extent possible. Fine. So, what we do is, first of all we think what are the pendant atoms and what is the central atom. In this case BH2, B is the central atom, right, and the hydrogen atoms are the pendant atoms. You know what is the meaning of pendant? Sometimes girls wear rings, chains, and then there is a locket. The locket is also called pendant. Pendant means something that hangs at the end. Okay. So, the hydrogen atoms are the pendant atoms. Which orbitals of these pendant atoms are likely to participate in the bonding? Which S? 1s, right. So, what I will try to do is, I will try to see in how many ways I can arrange these 1s orbitals. Okay. So, one that I can think of is plus and plus. The other that I can think of is plus and minus. Can you think of any other combination? Minus and minus is just minus of plus and plus, and minus and plus is just minus of plus and minus, right. So, these are the two basic combinations. These are the SALCs, symmetry adapted linear combinations. They are mathematical constructs of the atomic orbitals of the pendant atoms. What we do is, we construct them, look at their symmetry, and then we try to find, let me finish the sentence, we try to find orbitals on the central atom that would match these symmetries, and then we only consider combination of the SALCs and the central atom orbitals that have matching symmetries. Yeah.
What do we represent by minus sign?
Okay. What do we represent by minus sign? Do you remember what is the shape of, do you remember this radial distribution function of 2s orbital? 2s. If you just take a section through 2s orbital, it looks like this. Why does it look like this? Because in the expression for the wave function, there is something like 1 minus, no, r minus, and the a by 2a0 or something, 1 by, no, what am I doing? 1 minus r by 2a0, right? 1 minus r by 2a0, right? Multiplied by whatever it is. Now, when you equate this to 0, when will the wave function be equal to 0? When r equal to 2a0. So, this is where it becomes 0, and that is where it changes sign. Okay. So, this is called what? What is it called? It is called a node. A node is a point where wave function changes sign. So, this plus or minus is just the sign of the wave function, nothing else. If you think of a simple sine wave, the value is plus here and the value is minus here, isn't it? So, it is also called the phase, plus phase and minus phase. No node in 1s. But what I can do is, I can draw 1s like this, or I can draw it like this. Who is going to stop me? I am taking linear combinations, no? When I take linear combination, I can just add a minus sign.
So then there should be 4 types of combinations of 2s.
What was that? Yes.
Because for one structure the plus and minus are different.
So, see what I have done. I have taken a combination of plus and minus. Here I have taken combination of plus and minus, right? If it is 2s, then what will happen? This is one combination. Now I think your answer. Alright. So, in fact, this node in 2s has very important implications in your hybrid orbitals. Once again, I digress a little bit, but does anybody remember the shape exactly of sp orbital? If I ask you to draw the contour for sp orbital, what will you draw? I will draw it for you. Get this back. we'll use that also. Maybe today we'll run out of time, but tomorrow we'll need it. If I ask you to draw the contours of sp orbital, this is what you always draw. Remember this? This is plus, this is minus. My question is, where is the nucleus? Here? Then? Somewhere here. Why? Because what are you mixing? You are mixing 2s and 2p, right? What is 2s? 2s has a node, right? So let's say this is minus, outside only you have plus. So once again, take a section. This is what 2s is going to be, something like this, minus close to the nucleus and plus away from the nucleus. What about p? What about 2p? 2p is something like this, right? It is 0 at nucleus, right or wrong? Cross section of 2p. You know what 2p looks like anyway, right? I just taken a cross section. So 0. Now see, in the immediate vicinity of the nucleus, it is the value of 2s that is going to predominate, not 2p, because 2p is just 0, right? So add 0 to a negative quantity, you get a negative quantity. So in the immediate vicinity of the nucleus, it has to be minus, no matter whether you are on this side or whether you are on this side. All that happens is that on this side, this okay, what happens on this side? Let us see. What did I just draw? The other side of 2s, right? So when you go far away from the nucleus, here on this side, this plus and minus start cancelling each other. Okay? You get destructive interference. That is why this lobe is so small. Because far away from the nucleus, this has a large positive value, 2s, 2p has a large negative value. They cancel each other. But in the immediate vicinity of the nucleus, on both sides, 2p has a negative value, 2s has a value of 0. So it will be 0 all the way. And if you go this side, you have constructive interference all the way. That is why you have a bigger lobe here, because here values are being added up. Maybe next day I will bring you a nice cartoon where it shows how 2s and 2p mix and sp is formed. I will show it to you next day. Okay, but we just digressed. Let's come back here. We are talking about BH2, and we said that we can have two kinds of combinations of the 1s atoms of the pendant hydrogen, 1s orbitals of the pendant hydrogen atoms, right? Now, what are the AOs that have the right symmetry to combine with these SALCs? What are the atomic orbitals of beryllium? Beryllium 1s, what is the electron configuration of beryllium? 1s2, 2s2? That's it, right? But then 1s is much lesser in energy. We can consider 1s to be non-bonding completely, not participating in the bonding. So 2s, 2p, right? Only a valence shell, what? Yeah. 1s energy is much less, right? So only the valence shell reacts, isn't it? So we only concern ourselves with valence shell usually. I'm sorry? 2s? It is 2s2, right? So what is the valence shell? It is 2. So 2s and 2p can actually contribute. Now, does 2s match the symmetry of any of these? And 2p matches the symmetry of this. Right? Plus plus, minus minus. Right? So now what we are saying is, first of all, we will construct the SALCs. What are the SALCs? I will write like this: psi SALC equal to sum over I, what should I write? Ci psi pendant. Psi I pendant, so something like that. Sum over I, Ci psi I of, I'll just write Pa. Pa means pendant atoms. Alright, that is what I did first. I took the 1s orbitals of the hydrogen atoms and made linear combinations. And then psi MO should be equal to A psi AO of the central atom, which is written as M, plus B psi SALC. This is how I am going to construct my molecular orbitals. The approach we are taking is basically linear combination of atomic orbitals. Yeah.
Who is there in the subscript
Where?
for psi SLC?
Here? No, no, no. This is different, something different. 2s is the label for this. You want me to write in a little neater way, I can do that. SALC approach, what you do is, you construct the symmetry adapted linear combinations from the atomic orbitals of the pendant atoms that are likely to participate in bonding. And then you say that you construct the molecular orbitals by taking an appropriate linear combination of the psi of the central atom plus the SALC. Okay. What is the combination? What is the restriction? This psi central and psi SALC must have matching symmetries. In the language of group theory, they must belong to the same irreducible representation. Okay. So we said that, and then what we said was, so first of all I am going to take these linear combinations. Plus plus is 1 and plus minus is another 1. 2s of beryllium has the right symmetry for this plus plus combination. 2p of beryllium has the right symmetry for the plus minus combination. But whatever I have drawn here is basically bonding interaction. You can have anti-bonding interaction also. How will I get the anti-bonding interaction? I can keep the central atoms the same, central atom AOs, but I can change the sign of the SALCs. Instead of plus plus, I can write minus minus, and what all that it means is that B has become minus B, right? And this can become minus plus, something like that. Alright. So see, so far all this we can do without even bothering about your character table. Okay, that's why we are doing it first. What kind of MO will you get if you combine these? What will it look like? Something that is delocalized over all the atoms. What will this MO look like? It will look like the big sister of p orbital. No? All right, fine. So, and you know what the energy level should be in these cases. I'll just show you what you expect then. Out of these two, which one will be of lower energy? Huh? This one will be of lower energy, isn't it? Okay, what if I, no. Right. This one will be of lower energy. Now what have I done? I think I made some mistake somewhere. Suppose I take this, suppose I try to combine this with something else. Suppose I try to combine this with plus minus, then what will happen? And then suppose the same thing will happen there. So this is the kind of energy, order of energy that you are going to get, okay, that you can figure out. What? These are the atomic orbitals, these are the atomic orbitals of pendant of the central atom. You combine them, I think you know how to construct the energy diagram. Fine. Now the thing is, we don't want to leave it as qualitative as this. Eventually we want to know how we can use the character tables to do this.